Here's a section that I think is important beyond compare, but a true understanding of it is typically not had until you've had a higher level, more theoretical course in calculus. But this is so crucial that if you understand it, a great deal of calculus falls right at your feet just by understanding the mechanisms that are involved here. I'm going to start with a few things, and uh, well, I'll go as I do examples to try to explain what I'm doing. So I want you to consider the set. Here, I'm going to write a set of numbers here. 0 0.9, 0 0.99, 0 0.999, 0 0.9999, and this goes on forever and ever and ever. Now, my question to you is, what's the biggest number in the list? Well, you might say, if you try to pick something, they have to have nines, all nines in the decimal expansion. That's the way the set is designed. So what's the biggest number? Well, the biggest number, you'd want to say 0.999. I don't know how many nines you'd put in there, but you have to realize that no matter where you stop, there's always a number bigger than that with an extra 9 after the one you stopped at. So really, this goes on forever. There's no number out there that's actually in this set. So what is the biggest number in the set? I'll just say n/a. There is not a biggest number. These numbers go on forever. However, the number 1 is bigger than any number in the set. So 1 is called an upper bound. So an upper bound is simply a number that's bigger than any number in the set that you're given. So the number 1 is an upper bound. Now, next, can I find another number less than 1 that is also an upper bound? Can I find another number besides 1, maybe less than 1? Can I find a number less than 1 that's bigger than every single number in this set? So, well, what do numbers less than 1 look like? Well, a number 1, numbers less than 1. Let's write the decimals. Okay, so if we look at for decimals, we could have numbers like this. We could have 0.9, you could have 0.8, you could have 0.7. Any of these things are less than 1, but the problem is that none of these are bigger than every number in the set. So, you could see any number that it would be of these forms has no chance. So I'd have to start doing 0.9s. Can I come up with a number that's less than 1? So I would have to go until I got to, say, the nth decimal place. I would have to put nines in n decimal places, what I'd have to try to settle on. But the fact is, then unfortunately, it's not bigger than every number in there because another number that's bigger than it, I can simply go, n plus 1 places. So what we have then, thus, the number 1 is the least upper bound for the set 0.9, 0.99, 0.999. So basically, you're looking for the smallest number that's at least as big as everything in the set, but no other number smaller than it will work for this particular purpose. That's what a least upper bound is. So let me define some things, and then we'll go on with this. You might have remembered also that this here, 1 happens to be the limit of this particular sequence of numbers. In fact, remember, one of the ways you wrote this was 9 times 10 to the negative 1, 9 times 10 to the negative 2. Sorry, let me erase that plus. Or what looked like this, the sum k equals 1 to infinity, 9 times 10 to the negative k. And I showed that that was equal to 1. But you also kind of have to arrive at it because, 1, while it's not in this particular set, there's no number smaller than this that could be a lower upper bound. And it just so happens that 1 is the limit of these numbers, which will happen quite often. So let me put this is equal to 1. So let's put this way. Let S be a non-empty set of numbers. Okay, the number U is an upper bound for S if U is greater than or equal to X for all X in the set S. So U is bigger than every single number, or at least as big as every single number, then it's called an upper bound. Then L is called the least upper bound for S if L is less than or equal to U for every upper bound U. Then what we have is the axiom of the least upper bound says that any non-empty set of real numbers with an upper bound has a least upper bound. this here is an interesting statement in that I'm using the phrase axiom. I'm not using theorem or anything like that. The reason for the word axiom is an axiom is something that we accept as true without proof. So we are accepting that if I have a non-empty set of real numbers and they're bounded above, then they have a least upper bound. Let me do a few examples to sort of convince you that that's true. So, for example, let's take a look at this one. If you look at the set 0, 1, okay, 1 is the least upper bound. I'm going to start using that notation for least upper bound. 1 is the least upper bound because it's the smallest number that's at least as big as everything in here. Even if I had a closed interval that included 1, 1 is still the least upper bound. If you had to set something like this, 0, 5, union 6, 8, union 10 to 30. Well, the least upper bound will equal 30. And while we're at it, something called the greatest lower bound will equal 0. The greatest lower bound is an analog, but it's the largest of all the lower bounds. So you can go and use it. Although we won't use that directly in what we're doing in this class. Here, try this one. Let's see. S sub n equals 1 minus 1 over n. Then if you look at the set of S sub n's, where n equals 1 to infinity, start looking at these. When n is 1, that means S sub 1 is 0. When n is 2, I get 1/2. When n is 3, I get 2/3. You can see the sequence is approaching 1 as n goes to infinity. Well, it also happens that this has 1 as a least upper bound. You can go the other way too. In this version of it now, you can see that as n gets bigger, I'm getting 1 plus 1/2, 1 plus 1/3, 1 plus 1/4. This is approaching 1 also. So this set, this what you'd call an increasing set, has 1 as a, this is a decreasing set. This is going down to 1. So it has 1 as a greatest lower bound. Just keep in mind that the greatest lower bound and least upper bound are analogs. One happens at the top and the other happens at the bottom. Okay, so this brings me to how it's going to be used in this course. So we'll say suppose S sub n equals 1 to infinity, an increasing sequence of positive numbers. So stop right there for a minute. If I'm saying it's an increasing sequence, that means I require that S sub n is less than S sub n plus 1 for every n. All right, so it's increasing. That's what that means. Next, suppose S sub n equals 1 to infinity, has an upper bound. Okay, then by the axiom that I said, then let L equal the least upper bound of all of those numbers. Then my claim is that the limit as n goes to infinity, s sub n equals L. And I guess I'll do a proof of it. You get an idea of how these things work. You might have uncontrollable shivers when you see what I'm going to write first, but relax and just let it wash over you. Let epsilon greater than 0 be given. So remember, epsilon typically is a small number of some sort, and it's used in all the limit proofs use it one way or another. Since L is an upper bound, it's the least one, but it is also an upper bound, we know that S sub n is less than L plus epsilon for every n. I know that for a fact because S itself, well, let me just put it here, Sn is less than or equal to L, so it's definitely going to be less than L plus a positive number. So I'll put a little implication symbol there. So we know that S sub n is less than L plus epsilon for all n anyways. On the other hand, we cannot have S sub n being less than L minus epsilon for all n. Because if we did, then L minus epsilon would be a smaller smaller upper bound for S. So we can't have that. So we cannot have this. Thus, there is at least one n in the natural numbers with L minus epsilon less than Sn. But now, since S sub n is an increasing sequence, S sub capital N is less than S sub capital N plus 1, it's less than S sub capital N plus 2, it's less than S sub capital N plus 3, and that goes on and on and on. In other words, so for every n greater than this particular capital N, S sub n is greater than L minus epsilon. So now we have it. Therefore, this is the final step here. For every little n greater than n, I have L minus epsilon is less than S sub n is less than L plus epsilon. Here, I needed a certain size of n to ensure this part of it, but this other side was guaranteed. And this is the same thing. I'll put this. If you've ever seen this as a if and only if or dual implication statement, Sn minus L is less than epsilon for all n greater than n. What that means then is that the limit as n goes to infinity, S sub n equals L. And that is why all of our theorems about infinite series are going to work out, because we're going to be looking at something like this. At least initially, most of the stuff we do initially is going to be doing this. Sn will be a sequence, but its terms will be these things. And we're going to assume, for the most part, that these a's are all positive numbers. So if a sub k is always positive, then S sub n is an increasing sequence. It's easy to see that because Sn will equal the sum from 1 to, it doesn't matter where it starts at, so I may just start dropping that. I may start dropping the k equals 1 to infinity and just putting a summation sign and dealing with it that way. But it doesn't go to infinity, it goes to n. Well, since all of the AKs are positive, this is less than itself. I don't know what a sub n plus 1 is. All I know is it's positive. And that there equals s sub n plus 1. So the sequence is increasing. Thus, whenever we know that the summation k equals 1 to infinity, say a sub k, is finite, that means that the SNs are going to be bounded by some number. So you could say, I don't know what it is. All I know is it's less than infinity. Say, you know that a sub k, I'm going to start dropping them now, is less than some capital M. All I care about is it has a bound of some sort. This will imply that S sub n will be less than M for all of the n's. Well, if that's true, we have an increasing sequence that is bounded above. What did I just say above here? Then that sequence has a limit. Therefore, the sum exists. So let's write that out. S sub n is a sequence of increasing numbers so it is bounded above. A sequence of increasing numbers which is bounded above. So, limit as n goes to infinity, S sub n exists. So some number is equal to that. Therefore, there I'll do the symbol again, therefore, summation k equals 1 to infinity a sub k exists, or is convergent. So this is the technical aspect of what we are going to do. I'll try to reinforce this with each of the series examples that I do that involve positive numbers. It's a crucial concept. It's one of those things that, for most people, I'll be honest, it'll be years from now if you decide to go on in math, you'll be in some advanced calculus class or higher, and all of a sudden it will hit you like a ton of bricks. You'll be like, oh, that's what that meant. Unfortunately, things go so fast in calculus, it's difficult for it to set in now. But if you get an inkling of the feeling, you're on your way.